Section 1 Introduction. Today, large language models, LLMs, are transforming the AI landscape. Their development is driven by factors such as increased data input, heightened computational processing power, and larger model sizes. These advanced LLMs demonstrate capabilities not seen in smaller models, such as learning from context, following instructions, and logical reasoning. Intriguingly, LLMs may also have the ability to connect linguistic symbols with real-world entities, opening the door to artificial general intelligence, AGI, applications, like self-guided language models capable of manipulating tools, and generative agents in interactive virtual environments. However, these models come with their challenges. Since LLMs learn from both high and low-quality data, they can exhibit unintended behaviors, such as inventing false information, producing biased or harmful content, or even generating toxic text. To counteract these issues, it's vital to align LLMs with human values, making them helpful, honest, and harmless, the 3 H's. The emergence of open-source foundational models has greatly accelerated LLMs' development, bringing us to a stage where the models are fine-tuned through supervised learning. To reduce the risk of harmful behavior, many current approaches attempt to integrate these 3 H values during the fine-tuning process. The idea is to encourage the models to exhibit positive behavior at the ethical and moral levels. However, despite incorporating safety measures and groundedness objectives, current LLMs still fall short of human-level performance in these aspects. Therefore, there's a pressing need for more effective control mechanisms to mitigate potential risks associated with LLM use. Some promising work has been done by organizations like OpenAI and Anthropic. They have demonstrated that RLHF, reinforcement learning from human feedback, can be a valid method to align language models with user intent across a wide range of tasks. Training LLMs to align with human values using RLHF, though, can be quite challenging and often results in failure. Successful RLHF training necessitates a precise reward model that acts as a stand-in for human judgment, careful hyperparameter exploration for stable parameter updating, and a robust PPO, Proximal Policy Optimization, algorithm for reliable policy optimization. However, if the reward model is trained with low-quality data or if the alignment target is poorly defined, it can misguide the PPO algorithm, making training and scaling difficult. In our work, we thoroughly examine the RLHF framework and discuss the entire process that influences the success of the algorithm's training. We explore how the quality of the reward model impacts the final outcome of the policy model. Our findings suggest that the quality of the reward model sets an upper limit for the policy model's performance, and designing a suitable PPO algorithm is crucial for successful RLHF training. We suggest monitoring the PPO training process with metrics derived from the policy model, such as perplexity, response length, and KL divergence between the policy model and the supervised fine-tuning model. These metrics provide more useful insights about training stability compared to response reward and loss function values. Based on our observations, we find that policy constraints within the PPO algorithm are key to achieving consistent alignment with human preferences. After extensive experiments with various implementations of the PPO framework, we introduce a refined policy optimization algorithm, PPO Max. This improved algorithm incorporates the most effective implementations and is calibrated to avoid any interference among them. PPO Max enhances the stability of traditional PPO training and allows for longer training periods with larger datasets. We have tested PPO Max on 7B and 13B supervised fine-tuning models, demonstrating alignment performance on par with ChatGPT. Our contributions can be summarized as follows. 1. We provide high-performing Chinese and English reward models that can generalize well across different models, reducing the need to relabel human preference data. 2. We conduct a detailed analysis of the PPO algorithm's inner workings and introduce the PPO Max algorithm for stable model training. 3. We provide the complete PPO Max codes, enabling current supervised fine-tuning stage LLMs to better align with human values. Section summary. Large language models, LLMs, have shown remarkable progress in AI, but they also pose risks such as generating biased or harmful content. To align LLMs with human values, researchers have explored reinforcement learning from human feedback, RLHF, but training LLMs using RLHF is challenging due to the need for accurate reward models and stable parameter updating. In this report, we dissect the RLHF framework, discuss the importance of the reward model's quality, propose a robust PPO algorithm called PPO Max, and release competitive reward models and code implementations to improve the alignment of LLMs with human preferences. Section 2 Related work. In this paper, we are focusing on refining large language models, LLMs, to ensure they adhere to the principles of being helpful, honest, and harmless, referred to as 3H. These are important guidelines because these models can sometimes exhibit unintended behaviors like creating biased content or even fabricating information, largely because of the low-quality data used in pre-training. Current research tries to include 3H compliant data during fine-tuning, aiming to steer these models towards ethical and moral responsiveness, but we are still far from achieving human-like levels of safety and groundedness. We need better strategies to control these models and minimize any potential risks they pose. One popular method to make these models align more with human values is through fine-tuning them to learn and simulate human preferences. This approach needs the model to take in a context, along with several suffixes rated or scored by humans, and generate human-like results. An effective way to accomplish this is through reinforcement learning, RL. In this scenario, our model, or agent, learns from a limited amount of guidance received from the reward model, which acts as a stand-in for human judgment. This agent is then adjusted over many iterations under the framework of reinforcement learning from human feedback, RLHF. Several recent studies have adopted this method, especially for LLMs, in an attempt to make these models more helpful, honest, and harmless, hence reducing the negative impact they might have on society. For instance, Lambda is an approach that fine-tunes these large language models to enable them to take part in natural language dialogues that are interesting, helpful, and factually accurate. Instead of using reinforcement learning, it utilizes a combination of supervised learning methods for aligning with human preferences. Another initiative, Instruct GPT, fine-tunes models similar to GPT-3 to enhance their usefulness, merging this with RL that's based on human preferences expressed via comparisons. Some methods use pre-training and fine-tuning to train preference models for alignment with human values. This approach asserts that ranking preference models is an efficient way to distinguish between good and bad behavior. A further improvement to this method is continual training in an online setting, where preference models and RL strategies are updated weekly using new human feedback. This process also incorporates Proximal Policy Optimization, PPO, to stabilize RL training. While effective, RLHF and especially PPO can be complex and sensitive to hyperparameters. Although many studies have acknowledged the importance of PPO and attempted to enhance its efficiency, the issues of instability and sensitivity have yet to be fully addressed. Certain researchers reveal that the rewards from PPO may come from small adjustments to the base algorithm, while others claim that many low and high-level design decisions crucial for performance are often overlooked. This paper aims to delve into the framework of RLHF and shine a light on the workings of PPO. We aim to develop an advanced version of PPO that can significantly improve the stability of the policy model's training. Section Summary. Language models, LLMs, have the potential to generate biased or harmful text, so it is important to align them with human values. Most current approaches involve using human feedback to train LLMs, but they still fall short in terms of safety and groundedness. Reinforcement learning from human feedback, RLHF, is a promising solution, where LLMs are trained to align with human preferences through a reward model. However, RLHF can be complex and unstable, so this paper explores an advanced version of RLHF that improves training stability. Section 3. Reinforcement learning from human feedback. In this section, we delve into the concept of reinforcement learning from human feedback, RLHF. The method we employ to train an AI assistant consists of three major steps: supervised fine-tuning, SFT, reward model, training, and policy optimization using the Proximal Policy Optimization, PPO, method. In the first step, SFT, the AI model learns how to engage in human-like dialogues by copying human annotated dialogue examples. Then, in the reward model training phase, the AI model learns how to evaluate and compare different responses based on human feedback. Finally, during the PPO phase, the model is refined based on the feedback from the reward model, with the aim of uncovering an optimized approach by striking a balance between exploration and exploitation. In the RLHF method, we focus on the stages of reward model training and reinforcement learning using PPO. This PPO algorithm unfolds in a series of steps as illustrated in the provided figure. For the architecture of the reward model, we employ pre-trained transformer-based language models. The final unembedding layer is removed and replaced with an additional linear layer. This model assigns a reward value to the last token of any given text, with a higher reward value indicating a better sample. Training reward models usually involves using a dataset that contains comparisons of two responses generated for the same input, as per the methodology outlined by Stienen and colleagues. We quantify the loss for each pair of preferred and non-preferred samples using a mathematical formula, which employs the sigmoid function to calculate the difference in rewards between preferred and non-preferred responses. Furthermore, we introduce imitation learning to model preferred responses for each sentence pair. We apply a coefficient to the loss of the language model to regulate its impact. The loss in our reward modeling is defined using a formula that combines the log of the sigmoid function applied to the reward difference and the log of the reward for the preferred response, multiplied by the coefficient. We also add an extra term to the reward function, which imposes a penalty based on the Kullback-Leibler (KL) divergence between the learned policy and the initial supervised model. This reward is given by a mathematical formula that subtracts the product of the KL divergence and a coefficient from the reward of a given response. The inclusion of the KL divergence serves two important purposes. Firstly, it promotes exploration within the policy landscape and prevents the policy from settling into a single mode too soon. Secondly, it ensures that the output of the learned policy does not significantly diverge from the samples encountered during the training phase of the reward model. Section Summary. The training process of the AI assistant involves 3 stages: supervised fine-tuning, reward model training, and proximal policy optimization. During supervised fine-tuning, the model learns to engage in human-like dialogues by imitating human annotated examples. In the reward model training stage, the model learns to compare different responses based on human feedback. Finally, in the proximal policy optimization stage, the model is updated based on feedback from the reward model to discover an optimized policy. Section 3.2 Reinforcement Learning. In the section titled 3.2 Reinforcement Learning, the authors discuss the challenges associated with applying reinforcement learning (RL) to dialogue generation due to the expansive state action space. In this context, we consider the human interaction as the environment. At each point in time, the AI assistant, which we refer to as the agent, receives a state. This state is the cumulative history of the dialogue up to that point, encompassing both the AI assistant's and the human's responses. Then, based on a predetermined policy, the agent takes an action, which involves generating the next word or sentence. The environment responds by providing a reward calculated from a reward function trained on human preference data. The agent then transitions to the next state, which includes the updated dialogue history. The objective of RL is to find the best strategy for the agent, allowing it to maximize the total reward over the entire trajectory, which is a sequence of states and actions. There are 2 types of returns. The first type is a finite horizon undiscounted return, simply the sum of rewards gathered within a set number of steps. The second type, the infinite horizon discounted return, considers all rewards acquired by the agent throughout its entire trajectory but discounts future rewards using a factor that lies between 0 and 1. Moving on to subsection 3.2.1 Policy Gradient Methods, the authors discuss policy gradient methods. These are a type of RL techniques that optimize the policy, the map of states to actions, directly rather than learning a value function. These methods improve the policy by moving its parameters in the direction that boosts the expected return maximally. The policy, which gives the probability of taking a specific action in a given state, is characterized by a parameter we'll refer to as theta. The policy gradient, the rate of change in policy performance, is used to adjust theta, using a learning rate factor. There are several ways to calculate the policy gradient, but all lead to the same expected value for the policy gradient, though they might have different variabilities. This variability is due to the fact that different trajectories can have diverse returns because of the random nature of the environment and the policy. To reduce this variability, an advantage function, which measures how much better it is to take a specific action in a given state compared to the average quality of actions at that state under the same policy, is often used in place of raw returns in the policy gradient update rule. The advantage function is mathematically defined as the difference between the action value function, which represents the expected return after taking a specific action in a given state, and the value function, which is the average expected return at a given state. The use of policy gradients with advantage functions forms an essential part of RL. But, the ways the advantage function is estimated can vary significantly across different algorithms, leading to a variety of approaches. In the next section, the authors will introduce generalized advantage estimation, a method that underpins policy optimization algorithms and is widely used. Section Summary. Reinforcement learning, RL, is challenging in dialogue generation due to the large state action space. RL treats human interaction as the environment and the AI assistant as the agent. The agent receives a state from the environment, dialogue history, takes an action, generating the next token, and receives a reward based on a reward function trained from human preference data. The goal of RL is to find an optimal behavior strategy to maximize cumulative reward. Policy gradient methods directly optimize the agent's policy, mapping of states to actions, using gradient ascent, adjusting policy parameters to improve expected return. These methods can use advantage functions to reduce variance and estimate how much better it is to take a specific action at a state compared to the average quality of actions under the same policy. Generalized advantage estimation, GAI, is a widely used method for estimating advantage functions in RL. Section 3.2.2 Generalized Advantage Estimation. We are now delving into the concept of generalized advantage estimation, also known as GAI. This approach is designed to address an essential issue we face when estimating the advantage function. As a reminder, the advantage function, denoted by A, represents the difference between the Q function, which is the expected return for a specific action, and the value function, which is the average expected return for all possible actions as determined by our policy. In practice, when we want to estimate the Q function, we use the total reward from actual episodes, but this method introduces a lot of variability because the rewards we'll get in the future can be unpredictable and full of noise. To help reduce this unpredictability, we can estimate future returns using the value function after a particular time step. This is where the generalized advantage estimation (GAI) algorithm steps in. It helps strike a balance between using a single-step temporal difference (TD) returns and full Monte Carlo returns, thus controlling both the bias and the variance. In essence, a TDK return is a mix of the real rewards we get and our estimated future returns. It's like saying, our expected return at time t after k steps is the sum of the discounted rewards we got until k steps plus the discounted estimated return at the kth step. The gamma we talk about here is the discount factor, a way of ensuring that immediate rewards are more valuable than distant ones. With this, we can calculate the k-step advantage. This is essentially the TDK return minus the value of the state at time t. If the k we use is small, the estimation can be biased because it's based on fewer steps and relies heavily on the accuracy of the value function. However, if k is large, the variance can be high because the estimation involves summing up many noisy rewards. To balance this bias-variance trade-off, GAI comes up with an advantage function that's an exponential moving average of k-step advantages. It uses a parameter, lambda, as the weight, which influences how much emphasis we put on the recent rewards. You can visualize it as a weighted sum of TD errors, where the weight decreases exponentially with the number of steps. The sum is multiplied by 1 lambda, and lambda controls the trade-off between bias and variance in our estimator. This GAI method allows us to transition smoothly between high bias, when lambda equals 0, and high variance, when lambda equals 1, estimators, effectively managing the trade-off. By using GAI, we can estimate the advantage function accurately. This estimate is crucial when building a policy gradient estimator, which aids in learning the optimal policy. The policy gradient estimator is essentially an average of the gradients of the log probabilities of the actions multiplied by the estimated advantage over all time steps and all trajectories in a batch of samples. In summary, GAI helps us estimate the advantage function more effectively by striking a balance between bias and variance, thus improving the performance of our policy gradient algorithms. Section summary. The generalized advantage estimation (GAI) algorithm is a method used to estimate the advantage function, which measures the difference between the expected return and the expected return from following a policy. GAI balances bias and variance by combining actual rewards with estimated returns, using a combination of actual rewards and estimated returns to reduce noise and find a middle ground between one-step and full Monte Carlo returns. This estimation is crucial in constructing a policy gradient estimator for reinforcement learning. Section 3.2.3 Proximal Policy Optimization. In Section 3.2.3, the paper discusses Proximal Policy Optimization, PPO, a crucial technique used in reinforcement learning, RL, along with Trust Region Policy Optimization, TRPO. These strategies are designed to guide a policy towards optimization without endangering its stability. Their underlying principle is akin to taking small, stable steps, rather than making significant, potentially disruptive alterations. This idea extends from traditional RL's policy gradient principle, which requires the new and old policies to stay close in their parameter spaces. However, this proximity doesn't necessarily translate into equivalent performance. A minor change in parameters could lead to substantial variations in policy effectiveness. Furthermore, if we make a big, unchecked step, it could trigger a severe drop in policy performance, something commonly referred to as falling off the cliff. This risk factor restricts the sample efficiency in basic policy gradients. TRPO offers a solution by imposing a unique kind of restriction on policy updates. It controls the changes in policies by ensuring that a measure of divergence between two probability distributions, called the KL divergence, remains within a certain acceptable boundary, This implies the updates are designed such that the difference between the new and old policy doesn't exceed a certain limit, ensuring the learning process stays stable. PPO, a variant of TRPO, further splits into two types: PPO penalty and PPO clip. While TRPO enforces a hard boundary on the KL divergence to avoid harmful updates, PPO penalty takes a different route. Instead of using constraints, it tackles optimization problems by incorporating a penalty-based approach. This is done by introducing a penalty factor that is multiplied with the KL divergence between the old and new policy, and this penalty term is subtracted from the objective function, thereby maintaining stability and preventing drastic changes. Section Summary. Proximal Policy Optimization, PPO, and Trust Region Policy Optimization, TRPO, are two important reinforcement learning techniques that focus on training policies effectively while maintaining stability. They achieve this by taking small, stable steps towards optimization instead of aggressive updates that can destabilize the learning process. While TRPO ensures policy updates stay within an acceptable limit by regulating the change in policies using the KL divergence, PPO introduces a penalty-based approach to address unconstrained optimization problems. Section. Clipped Surrogate Objective. Clipped Surrogate Objective. The Proximal Policy Optimization, PPO, algorithm introduces a strategy to ensure the new policy, which is the strategy that our AI model uses to make decisions, stays close to the old policy. This strategy differs from the approach of the Trust Region Policy Optimization, TRPO, algorithm, which uses a mathematical constraint on the Kullback-Leibler, KL, divergence. PPO instead uses a clipped version of the policy ratio in its objective. In simpler terms, we want our AI model to learn and improve, but not to change its strategy too dramatically from one step to the next. To do this, we compare the probability of taking an action under the new policy with that of the old policy, and we clip this ratio to lie between certain bounds. This clipped ratio, scaled by the advantage function, which measures how beneficial an action is compared to the average, forms the objective function. The advantage function essentially captures the relative goodness of an action in a given state, compared to other possible actions. The extent to which the new policy can deviate from the old one is controlled by a parameter, typically denoted as epsilon. The clipping serves as a form of regulation, preventing large, potentially disruptive changes to the policy from one learning step to another. This approach enhances the robustness of the learning process while maintaining more sample-efficient learning than traditional policy gradient methods. Value function estimation. In the PPO algorithm, we have a component called the critic model, or the value function, which is tasked with estimating the expected returns for each state. The expected return is the total reward that the model predicts it will receive in the future, starting from a particular state. The goal for training this model is to minimize the difference between its predicted values and the actual return values. To measure this difference, we use a common error metric called the mean squared error, MSE, which takes the square of the difference between the predicted and actual return values and averages these over all states. Mixing pre-training gradients. To avoid possible degradation in the model's language skills and retention of knowledge during the PPO phase, the paper suggests mixing in some pre-training data into the reinforcement learning (RL) phase. Models using this approach are named PPO-PTX. They aim to optimize a combined objective function. This function includes the previously discussed clipped objective from PPO, but also adds a component that measures the likelihood of the actions taken by the RL policy on the pre-training data. This likelihood is weighted by a coefficient, which controls the balance between the original PPO objective and the contribution from the pre-training data. This combination allows the model to maintain its language skills and knowledge while also learning from the RL environment. Section Summary. The clipped surrogate objective in PPO clip aims to keep the new policy close to the old policy by using a clipped version of the policy ratio in its objective function. This clipping acts as a regularizer, limiting drastic policy changes and ensuring robust learning while maintaining sample efficiency. In addition, the PPO algorithm incorporates a critic model, known as the value function, which estimates expected returns for each state and minimizes the discrepancy between predicted and actual return values using mean squared error. To further enhance language skills and knowledge retention, pre-training data can be incorporated into the RL phase by adding a pre-training loss term to the PPO objective function. Section 4. Reward modeling for helpfulness and harmlessness. In this section, we're discussing the concept of reward modeling, which is designed to mirror human preferences. Ideally, we would refine this model directly using reinforcement learning and human annotations. However, because of human time and workload limitations, it's impractical to get enough feedback before each optimization step. So, we found a more efficient way, creating a reward model, ERM, that imitates the evaluation process conducted by humans. We'll walk you through the technical aspects of the ERM, its performance in our experiment, and the changes we noticed in its performance during the training process. Let's start with the models and datasets we used. We initially used the Llama 7B, a decoder-only model, for English. Our training set consisted of 160,000 paired samples from the hydrogen hydride RLHF dataset, 118,000 of which were categorized as helpful and 42,000 as harmless. Out of the remaining 8,500 data points, we randomly chose about 700 helpful and 300 harmless examples, totaling 1,000, for our test set, and used the rest as a validation set. For Chinese, we incrementally pre-trained a model on Chinese datasets, building on the foundation of the Llama 7B. This significantly improved the model's understanding and generation capabilities in Chinese. We enlisted professional annotators to manually label 39,000 paired samples, which included 31,000 helpful and 8,000 harmless instances. For our training set, we randomly selected 24,000 helpful and 6,000 harmless instances. Then, from the remaining data, we randomly picked 2,400 helpful and 600 harmless samples to form our test set. The rest was used for validation. Now, let's talk about our training setup for the ERM. We used a learning rate of 5e6, with a warm-up period over the first 10% of steps. Instead of using a fixed batch size, we opted for a dynamic approach that tried to maintain an equal number of tokens in each batch, leading to more efficient and stable training. The batch size varied depending on the number of tokens in each batch, with a maximum of 128 and a minimum of 4. Our training process comprised around 1,000 steps, which corresponded to approximately 1.06 epochs for the whole training set. Throughout our experiment, we set the weight of language model, LM, loss, which we denote as beta_ERM, to 1 for training our reward model. Section Summary. In this section, the authors discuss the training of a reward model, ERM, to reflect human preferences. Due to constraints in obtaining sufficient human feedback, they propose using the ERM to emulate the evaluation process performed by humans. They provide technical details of the ERM and describe the datasets used for training and testing. Additionally, they outline the training setup, including the learning rate, batch size, and training steps. Section 4.3 Evaluation Results. In this part of our study, we share the results from evaluating our reward model, ERM, using the hidden human technique. To accomplish this, we took a close look at the model we trained, using a test set we've previously discussed. This test set consists of 900 samples of reinforcement learning with human feedback, RLHF, in English and 3,000 samples for Chinese, handpicked by professional annotators from the dataset. We applied these test inputs to our ERM to ascertain the reward value for the most and least desired responses. The difference between these values provides us with a difference score. The distribution of this score is depicted in a figure in our original document. The models we used demonstrated alignment with human preference to varying degrees. However, the ERM that was trained on our uniquely constructed Chinese dataset, courtesy of the annotators we hired, showed impressive consistency with human judgment. In reviewing the test samples that showed the most significant differences between the models and humans' preferences, we noted some interesting observations. For Chinese data, we found that the model rewarded longer responses more, even though these responses often included false claims and factual inaccuracies, which were less favored by humans. When it came to the English data, the model assigned lower scores to responses that acknowledged a lack of information. Although honest, these responses were less helpful, which seemed to be a negative factor in the model's evaluation. Interestingly, the model assigned higher rewards to responses that, while apparently correct and helpful, contained misleading or deceptive information. For illustration, we've included an example from both the Chinese and English datasets in our table. We also examined how the model performed over time during the training process. A figure in our document shows the trend in training loss of the policy model, PM. Notably, the ERM trained on the Chinese dataset performed better in terms of accuracy than the one trained on the English dataset. This was mainly because there was a clear distinction between the high and low quality responses in the Chinese pairs, while the quality of English responses was relatively similar, making it difficult for the model to discern superiority or inferiority. Consequently, both the training and testing accuracy for the English dataset was lower. Moreover, we found that the rate of improvement began to plateau after approximately 200 steps, or 0.2 epochs, for both models. The accuracy at this point was similar to what we achieved after a complete epoch of training. However, when we used the model from the 200-step point as the starting point for Proximal Policy Optimization, PPO, the results were underwhelming. Thus, we concluded that accuracy alone is not a sufficient indicator for the effectiveness of the ERM. Section Summary. The evaluation results of our reward model, ERM, show that it aligns with human preferences, especially for the Chinese dataset labeled by annotators. However, there are some disparities between the model and human judgments, such as the model favoring longer responses in Chinese and assigning lower scores to honest but unhelpful responses in English. The training performance of the ERM is better for the Chinese dataset compared to English, and the rate of improvement slows down after 200 steps. Accuracy alone is not sufficient as a criterion for the ERM. Section 5. Exploration of PPO. In this segment, we're diving into the intricacies of Proximal Policy Optimization, PPO, the central algorithm that helps us align with human preferences. There are many factors at play when applying PPO in real-world scenarios. Several studies in the past have highlighted some strategies that might be crucial and productive in the realm of reinforcement learning. However, it's still a mystery how to ensure stable training of reinforcement learning with human feedback, RLHF, with language models. We aim to investigate which strategies are key and which metrics can provide a glimpse into the state of the model both during and after RLHF training. We'll discuss the metrics that guide the training process and the training outcomes under various implementations to uncover essential strategies in RLHF. We label the best suited implementation we discover for the language model as PPO Max. Let's now look at our models and the training setup. The way we conduct training for the PM dataset and the preference model will be discussed later. Here, we will talk about how we initiate the models and the intricacies of the hyperparameters in PPO. As discussed later, 4 models need to be loaded during the PPO training phase. For the reference and policy models, we use a 7 billion parameter SFT, supervised fine-tuning, model as the starting point. This SFT model is fine-tuned using supervised learning for 2 rounds, based on 1 million filtered instruction data. This data comprises 400,000 single-round instruction samples and 600,000 multi-turn instruction samples. We assign a learning rate of 9.5 times 10 to the minus 6, which decreases over time following a cosine learning rate schedule until it's at 10% of the peak learning rate. We set the global batch size to 1024. To kickstart the critic and reward models, we use the reward model. The training is carried out on a manually built HH dataset, which contains 8,000 harmless queries and 20,000 helpful queries. Instead of determining the duration of training by the number of epochs, we fix the number of steps. Throughout all experiments, we fix the batch size to 128 for environment sampling and 32 for training the policy and critic models. The learning rates for these models are set to 5e7 and 1.65 times 10 to the minus 6 respectively, with a warm-up phase during the first 10% of steps. Our goal is to ensure stable convergence and superior results during the PPO training phase, so we've explored a variety of techniques in reinforcement learning. We conduct these experiments on a randomly chosen subset of our training data. We stop these experiments before reaching optimal results, once we've gathered enough information to compare the various methods. All experiments are carried out on machines with identical configurations, each equipped with 880 GB A100 GPS, 1 TB of RAM, and 128 CPUs. We employ 0-2 and gradient checkpointing techniques to minimize the GPU memory cost during the training phase. Section Summary. In this section, the authors explore the Proximal Policy Optimization, PPO, algorithm and its performance in aligning with human preferences. They aim to identify critical tricks and metrics for stabilizing reinforcement learning with language models. The authors introduce various training implementations, including model initialization, hyperparameters, and batch sizes, to ensure stable convergence and better results for PPO training. These experiments are conducted on identically implemented machines with specific GPU and CPU configurations. Section 5.2 Evaluation Metrics for Monitor Training Process. 5.2 Evaluation Criteria for Monitoring Training Progress. Our aim is to establish some standards that mirror the effectiveness of PPO training, which aids in observing the advantageous, trustworthy, and safe abilities of policy models without the need for manual or GPT-4 evaluations. It is indeed a complex task to accurately pinpoint the strengths of 2 models with comparable skills. Nonetheless, it's quite doable to monitor training consistency and quickly flag significant discrepancies. Various metrics curves, illustrating the ongoing optimization of the policy model using the basic PPO algorithm, are portrayed in the accompanying figure. First, we touch upon the concept of pattern collapse that occurs during standard PPO training. This denotes that SFT models are overtrained, leading to extremely biased behaviors. An ideal policy model should align with human preferences, mirroring the diversity of real-world dialogues, for instance, data not used in training the reward model. However, we have noticed that the trained policy model tends to trick the reward model into generating unusually high scores by repeating certain patterns. The graphs depicting reward scores and training losses during the PPO's training phase are presented at the top of the figure. While we observed stability in the training loss, higher rewards did not necessarily correlate with improved policy behavior, according to both human and GPT-4 evaluations. This indicates that neither reward scores nor training losses accurately reflect whether the PPO training is on the right track. In traditional PPO training, the reward responses of the policy model gradually veer off from the original distribution, presenting a long tail effect. We've depicted the distribution of these reward responses at various stages of training in the appendix. One practical approach is to contrast the training progress of well-performing and underperforming policy models to discern useful metrics. We have exhibited more revealing training metrics at the bottom of the figure, including perplexity, the KL divergence between policy and reference models, and the average length of generated responses. Earlier research suggested a near-linear correlation between the root KL and PM scores. However, this relationship appeared weaker for smaller models. We discovered that the model's response lands in the OOD, out-of-distribution, region of the preference model when the original policy is overtrained. We'll delve deeper into these scaling effects in the upcoming section. At the same time, we've noticed that the collapsed model consistently produces lengthier responses and exhibits lower perplexity for such generative patterns. We apply these metrics to highlight the significance of various techniques and their impact on PPO training in the subsequent section. Section Summary. The evaluation metrics for monitoring the training process of the PPO model are discussed in this section. The authors aim to identify metrics that reflect the quality of the training and track the performance of the policy models without manual evaluation. They observe the phenomenon of pattern collapse in vanilla PPO training, where the models become over-optimized and exhibit biased behavior. They propose various metrics, such as perplexity, KL divergence, and average response length, to evaluate the training process and compare good and bad policy models. Section 5.3 Implement details in PPO. Section 5.3 of our paper deals with the implementation details of Proximal Policy Optimization, PPO. We observe that the standard PPO algorithm often faces issues of instability and pattern collapse. This problem stems from over-optimizing the policy model, leading to fixed generative patterns. While previous research has explored the use of PPO in different scenarios, the contexts and data structures used in traditional reinforcement learning, RL, differ significantly from those in RLHF, which is our area of focus. Our aim was to check the suitability of various techniques in the context of language model training and introduce a version of PPO that allows for stable optimization. Our primary focus lies on methods that aid in PPO training efficiency and exploring their sensitivity to parameters. The paper discusses a multitude of tricks to facilitate PPO training. We first delve into the method of score reparameterization, then we discuss optimization constraints for the policy model, and lastly, we talk about different ways to initialize the policy in critic models. In our appendix, we discuss experiments related to hyperparameter tuning and other less critical tricks like advantage estimation functions and gradient clipping. The term score in our context refers to two key variables in PPO training: the reward score, provided by the model trained on human preference data, and the advantage score, computed using the generalized advantage estimation function. Our work has shown that reparameterizing these scores to a stable distribution like a standard normal distribution can enhance the stability of PPO. We checked our hypothesis through a series of tests. The tricks we tested include reward scaling, reward normalization and clipping, and advantages normalization and clipping. In the reward scaling technique, we controlled training fluctuations by scaling rewards. We divided the rewards by the standard deviation of a rolling discounted sum. Despite existing research claiming its efficacy, our findings revealed that this method did not guide policy optimization appropriately. Instead, it required stricter constraints for training stability. Reward normalization and clipping, a technique proposed by MNIH, was also tested. It processes rewards by clipping the normalized rewards within a certain region. Although often considered ineffective or even harmful in traditional RL, we found that strict advantage clipping could maintain training stability within a specific time frame. Notably, models with larger clipping thresholds displayed significant strategy changes and reached higher rewards later in training. However, achieving the best clipping bound within a limited number of trials proved to be a challenge, and we found some inconsistency between the reward model and manual evaluation results. we suggested using a relaxed clipping strategy and other tricks to limit policy optimization in RLHF training. Advantage normalization in clipping is similar to the reward operation but differs in its normalization level, which occurs only at the mini-batch level. Following the computation of the advantage based on the GUI, PPO normalizes the advantage value by deducting its mean and dividing by its standard deviation. Andrijevic first attempted this in the gaming domain, but it did not yield significant improvements. Although selecting parameters for advantage clipping may be challenging, our findings indicated that stricter constraints on advantage could provide similar effects to reward clipping in PPO training. Given the theoretical similarities between the effects of different score reparameterization techniques on PPO training, we recommend constraining policy optimization instability at the reward level. We also conducted experiments involving the combined application of reward, advantage, or value clipping operations, with the results discussed in the appendix. Section Summary. The section discusses the instability and pattern collapse problem of the PPO algorithm and explores different implementation details to address these issues. It introduces the score reparameterization method, which involves reparameterizing the reward and advantage scores to a stable distribution. The section also discusses the use of reward scaling, reward normalization and clipping, and advantages normalization and clipping to ensure training stability. The experiments show that tighter constraints are required for stable training and that a relaxed clipping strategy should be adopted when training RLHF. Section 5.3.2 Policy Constraints. Section 5.3.2 Policy Constraints to address the issue of over-optimization in the policy model. A useful approach is to limit the range of policy optimization. We've explored and confirmed the value of various strategies to manage the policy generation updates. Based on our empirical evidence, such constraints appear essential for longer training periods. Various methods and their corresponding parameters have been tested to assess their impact on policy optimization. One such method, known as token-level KL penalty, involves regulating the policy optimization by introducing a regularization factor. This factor is proportional to the KL divergence, a measure of the difference between two probability distributions, between the current and original policy distributions. This method, first proposed by Stienen and later adopted by multiple reinforcement learning-based human feedback (RLHF) systems, treats the distribution of output tokens as a sampling from the policy distribution. Using a template response pair, an empirically derived KL penalty sequence is applied to the response reward. The total reward, taking into account the KL penalty, is calculated using the following principle. The total reward for a given pair equals the reward for the pair minus a certain factor, denoted by eta, multiplied by the KL divergence between the reinforcement learning (RL) policy and a soft actor critic (SAC) policy for the response. Here, eta is a hyperparameter that needs to be finely tuned. Previous work by Anthropic used a small weight to adjust the balance between the reward and KL penalty during Proximal Policy Optimization (PPO) training. Their findings didn't highlight any significant effects on RL training. However, we found this constraint to be crucial for the stability of PPO, and it allowed us to extend the training steps. Results of our experiments with policy divergence penalties showed significant differences compared to the prior approach, particularly in later stages of training. Notably, we observed that RLHF improved the quality of the responses without significantly altering the language model. We also considered important sampling in PPO, which helps correct the divergence between the past generative model and the current model when optimizing policy models. Using a too large buffer can lead to incorrect estimations of the current policy's advantage, impacting the stability of policy optimization. By essentially having an infinite experience buffer in the training process, we found this setup to have less severe impacts than expected, though fluctuations did occur in later training stages. We also examined the impact of combining this setup with KL penalties, as they have similar controls on PPO. Our results showed this approach helped stabilize PPO training, but at the cost of the final performance of the policy model. Lastly, we looked into the entropy bonus method, which offers an independent constraint on PPO training. This method has sparked debates regarding its effectiveness across different scenarios. Some researchers, like MNIH, found that an entropy bonus could enhance exploration by encouraging policy models to generate more diverse actions. However, other studies found no clear evidence that such actions were beneficial. We believe both views can coexist since configurations regarding the entropy bonus are highly sensitive to parameter selection and implementation. Upon comparison, we didn't find a distinct advantage of the entropy bonus over the KL penalty. Therefore, we recommend using the latter, rather than directly limiting the diversity of the strategy space. Section Summary. To address the over-optimization problem in policy models, one solution is to constrain the policy optimization within a limited range. Different constraint methods, such as token-level KL penalty and entropy bonus, have been validated and shown to be necessary for longer training procedures. These constraints improve the stability of the training process and enhance the quality of responses without significantly modifying the language modeling. Section 5.3.3 Pre-trained initialization. In Section 5.3.3, we discuss the initialization of our models in the RLHF, reinforcement learning from human feedback, context. A common practice in RLHF is to kickstart the policy and critic models based on an existing reference model and a reward model. Such an initialization method has not been widely researched in the past, and its influence on PPO, Proximal Policy Optimization, training remains largely unknown. We set out to explore different initial setup methods during the early phase of model training, with a focus on the prerequisites RLHF imposes on a trained model's capabilities. Figure, not shown here, demonstrates the variance caused by different initialization techniques. Interestingly, the way we initialize the critic model doesn't significantly impact the convergence or the volatility of PPO. It mostly affects the numeric stability in the early phase of optimization. Conversely, if we initialize a policy model without prior supervised fine-tuning, SFT, training, we find it severely lacking in its PPO training performance. This suggests that having a well-established supervised policy model is critical in RLHF. In Section 5.4, we discuss our training implementations for the PPO max algorithm. Based on our earlier discussions and validations, we've picked the most effective strategy for each PPO component. Our process involves normalizing and clipping the present batch of rewards using historic mean and variance data. Then, we introduce a KL penalty term to limit policy optimization. During the model loading phase, we first initialize the critic model using our reward model, and we pre-train it before formally applying PPO. We employ global gradient clipping and keep a small experience buffer. To reduce what we refer to as alignment tax, we incorporate pre-trained language model loss in policy optimization similarly to Instruct GPT. We also clip the value function loss. For more intricate settings, you can refer to our open source code. A comprehensive display of the PPO max training dynamics is shown in figure, not shown here. In Section 6, we delve into the evaluation of our models and discuss our findings. We provide an in-depth analysis highlighting the advantages of RLHF models over SFT models. These advantages are clear not just in the direct comparison between RLHF and SFT models, but also in the performance gap when compared with ChatGPT. Section Summary. In the section, Pre-trained initialization, the authors explore the impact of different initialization methods on the convergence and stability of the Proximal Policy Optimization, PPO, algorithm in reinforcement learning from human feedback, RLHF. They find that initializing the critic model has minimal effect on PPO, while initializing the policy model without supervised fine-tuning, SFT, renders it ineffective in PPO training, highlighting the importance of a supervised policy model in RLHF. In the PPO Max Setup section, the authors describe their training implementations, including reward normalization, KL penalty term, critic model initialization, and pre-training language model loss. They provide a comprehensive analysis of the advantages of RLHF models over SFT models in the Evaluations and Discussions section. Section 6.1 Alignment Metrics and Experiment Setups. Section 6.1 Assessing alignment and setting up experiments. The concept of alignment, in the context of this study, is a bit nebulous and challenging to evaluate. Our aim is to align our models so that they align with human intentions. In simpler terms, we want our models to behave in a way that is both helpful and harmless. By helpful, we mean the model should be capable of following instructions, understanding the intentions behind a given prompt, and making relevant deductions. But it's not always easy to discern the exact intent behind a prompt, which is why we lean heavily on the judgments of our annotators. We use their preference ratings as a key measure in our evaluation process. The harmless aspect is equally difficult to quantify. The impact, or potential harm, of a language model largely depends on the context in which it's applied. For example, a model that generates offensive outputs could be harmful if integrated into a chatbot. Conversely, it might be beneficial in generating data to train a better model for identifying toxic content. So, we use a set of precise proxy metrics to assess various aspects of a model's behavior that could potentially be helpful or harmful. To draw a comparison between our RLHF models and the baseline models, we generate a single response for each test prompt. We then task human annotators to compare these responses from various models and indicate their preferences. We perform this experiment repeatedly, using GPT-4 as the annotator, and we consistently find a strong level of agreement between evaluations. For comparison, we have a few baselines in place, including 2 SFT models trained on llama datasets. These models have been trained on datasets in both Chinese and English. Additionally, we have developed 2 RLHF models from these SFT models using PPO Max, one trained on English text, marked as N, and the other on Chinese text, marked as ZH. Furthermore, we compare our models to OpenAI's ChatGPT, a highly effective language model that has been tuned with RLHF. Section Summary. In this section, the authors discuss the metrics and experiment setups used to evaluate the alignment of models with human intentions. They define alignment as models being helpful and harmless, where helpfulness is determined by the model's ability to follow instructions and deduce intent, and harmlessness depends on the real-world utilization of the model's outputs. To compare their RLHF models with baselines, they generate responses for test prompts and task human annotators to label their preferences. They also include baselines trained on Chinese and English datasets, as well as compare their models with OpenAI's ChatGPT. Section: Generation. Generation. For each given prompt, we generate a single response using a technique called nucleus sampling. We set a probability threshold of 0.9 and a temperature of 0.8 for our baseline models. To avoid repetitive responses, we introduce a repetition penalty based on previously generated tokens, with a hyperparameter value of 1.1. We also apply a length penalty with a value of 1.2 and limit the maximum token length to 2048. Scaling law. Although we primarily focus on a 7 billion parameter model in our study, we have not yet explored how the size of the model and the amount of data used impact the performance of RLHF, reinforcement learning from human feedback. Reward model. Our experiments are conducted using openly available English human preference datasets and a small amount of self-constructed Chinese data. However, the quality and quantity of the available data may not be sufficient for a comprehensive evaluation of the reward model. Evaluation metric. We mainly rely on manual evaluations and automated evaluations using GPT-4, but we have not extensively utilized various benchmarks and NLP tasks to conduct a detailed assessment of our models. Performance indicator. During the Proximal Policy Optimization (PPO) phase, our main focus is on achieving stability rather than maximizing the final performance. While stability is important, it does not guarantee improved outcomes. Furthermore, the reward score alone is not a reliable indicator for predicting RLHF performance during the training phase. Therefore, we need to explore alternative performance indicators that are more suitable for this phase. Section Summary. For generating responses, we use nucleus sampling with a probability threshold and temperature, while applying penalties to avoid repetition. We primarily focus on a 7 billion parameter model and haven't explored the impact of model size and data scale on performance. Our experiments use limited datasets, which may not be sufficient for a comprehensive evaluation of the reward model. We rely on manual and automated evaluations, but haven't utilized other benchmarks and NLP tasks. During the PPO phase, our focus is on stability rather than final performance, and the reward score is not a reliable indicator during training. A more suitable performance indicator needs to be found.